Tonight, the space above you sits at 454 degrees below zero, not in some distant corner of the galaxy, directly overhead, 100 miles up, closer to you than most cities. That's 2.725 Kelvin, less than 3 degrees above absolute zero, the point where all motion stops. And it isn't cold the way a winter night is cold. There's no frozen air, no wind, nothing there that could touch your skin at all. The cold of space is something stranger than that. By the end of tonight, you'll know how that faint afterglow of the Big Bang was found by two men who spent a year trying to scrub it out of their own data, and why everything warm and alive is a brief, improbable exception. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It helps this channel reach more curious minds like yours. The whole range of liquid water, the narrow band in which every living thing has ever existed, spans 100 degrees. The cosmos sits within 3 of the floor. Cold is not the exception. Cold is the default. Warmth is the rare accident. Most people picture that number by scaling up something they already know. A deep freezer turned colder than any kitchen appliance could manage. An Antarctic winter, stretched out until it swallows everything. The chill at cruising altitude on a long flight, deepened past anything a body could survive without a pressurized cabin around it. They're right that space is colder than all of that. They're wrong about how the cold actually works. The mistake is not in the scale of it. The mistake sits underneath, in the machinery. Cold is not a thing that arrives. Nothing crosses the room to reach you. Nothing pours in through a window. What we call cold is heat leaving, and heat leaves along a small number of fixed routes. Close those routes, and the word stops meaning what it used to mean. That is the piece almost nobody accounts for when they try to picture the temperature out there. Cold, as we feel it here, moves through 3 specific channels. Heat always flows from something warmer to something cooler, and it only ever does that through conduction, convection, or radiation. Conduction is direct contact, fingers on an ice cube, bare feet on a cold stone floor at 3 in the morning. Heat passes out of your skin because the two surfaces are touching, and touching is the whole mechanism. Convection works differently. A moving fluid, usually air or water, slides across a warm surface and physically carries the heat away with it. That is why wind makes a cold day feel colder than the thermometer claims, and why blowing across a hot bowl of soup cools it faster than simply waiting for it to sit. Both are things a body learns to recognize early. The bite of a draft through a doorway, the sting of stepping onto tile in bare feet, familiar enough that no one ever has to think about the mechanism behind them. Both of those depend on matter. Conduction needs a solid, a liquid, or a gas to move through. Convection needs a fluid to do the carrying. Neither one works on its own. Both need something physical in between the warm thing and the cool thing. Something to touch, something to move. Take away the matter, and both mechanisms stop functioning. Not gradually, but almost completely. That is exactly what space does. Not a little, almost entirely. Consider the numbers. A cubic meter of air in an ordinary bedroom holds something like 27 million trillion atoms. A cubic meter of interstellar space holds, on average, about 1. Not 1 gram of gas, 1 atom. The best vacuum chambers ever built on Earth, machines engineered specifically to remove as much matter as physics allows, still contain billions of atoms in every cubic meter. Engineers spend careers chasing emptier and emptier chambers, and even their finest result leaves billions of atoms behind, in a space where interstellar distance leaves only 1. Interstellar space beats the finest human vacuum by a factor so large the comparison stops feeling like a difference of scale, and starts feeling like a difference of kind. Push further out, into the vast voids between galaxy filaments, and the count drops lower still, sometimes below a single atom per cubic meter. There is, technically, no perfect vacuum anywhere in the observable universe. There is only emptier and emptier, all the way out. With almost nothing there, conduction has almost nothing left to conduct through. Convection has nothing left to carry. The two mechanisms that make a cold winter night genuinely dangerous, the ones a body has spent its whole life learning to guard against, are essentially useless in a vacuum. Not weakened, not slowed, useless. But here's where the everyday intuition breaks. The assumption underneath the whole comparison is that cold is cold, that space sits at the far end of a scale a body already understands. But if two of the three ways heat escapes a body simply do not operate out there, then whatever cold means in space, it cannot mean the same thing it means down here. Something else has to be doing the work. So what is left? Not touch, not moving air or water. What remains is radiation, and radiation plays by different rules entirely. Everything above absolute zero radiates energy outward as electromagnetic waves, whether or not anything is nearby to receive it. You are doing this right now. Sitting still, in a warm room, your body glows faintly in the infrared, releasing heat as a form of light your eyes were never built to register. The walls around you glow back. The furniture glows back. The net exchange between what you emit and what returns to you is the entire reason a room feels warm or cold, not the air temperature alone. Stand near a cold window on a winter night and you feel a chill even if the air in the room has not moved and nothing is touching your skin. That chill is radiation, your body losing more heat to the glass than the glass returns to you. Put a person in open space, and the outward half of that exchange keeps happening exactly as before. A body radiates heat continuously, the same quiet glow it produces sitting in any ordinary room, but almost nothing radiates back. No walls, no warm air pressing close, no surface near enough to return the favor. Heat leaves. Nothing obvious replaces it. Almost nothing. Not nothing. Because something does radiate back. Not from a wall, not from a nearby object, but from the emptiness itself. It fills every cubic meter of space, not just near planets or stars, but everywhere, in every direction, uniform and unbroken. It does not come from the sun. It does not come from any single star or galaxy. It arrives equally no matter which way an instrument points, as if the darkness itself had a temperature. It has been there for the entire span of time astronomers have pointed instruments at the sky, filling the same silence, waiting to be measured. Whatever it is, it means space is not simply empty and cold in the way a freezer is empty and cold. Something fills it. Something answers back. And that changes what cold even means out there. Two men were about to find it, and they were not looking for it at all. The year was 1964, and neither man was looking for an answer. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Laboratories in Holmdel, New Jersey, with a large horn-shaped antenna built originally for satellite communications. The satellite work had ended, and they had repurposed the antenna for something quieter, listening for faint radio signals drifting out of the Milky Way. Instead, they kept picking up a low, steady hiss they could not explain. It did not fade. It did not shift with the hour. Point the antenna anywhere in the sky, at any time of day, in any season, and the same hiss came back, uniform and unbothered, as if the instrument itself were broken. They assumed it was their own equipment. Radio astronomers spend careers hunting down noise, tracing every stray signal back to its source, so they went looking. New York City sat about 50 miles away, a plausible origin for stray radio interference, and they checked it and ruled it out. They checked nearby military installations. They checked a nuclear test site, in case fallout or radar leakage was the culprit. Nothing matched. Then, they found something more ordinary, sitting inside the antenna itself. A pair of pigeons had nested in its throat, and their droppings coated the metal surface where the signal was collected. Penzias and Wilson climbed up, removed the birds, scraped the antenna clean by hand, and pointed it at the sky again. The hiss was still there, identical, unmoved by any of it. Not a wiring fault, not the pigeons, not the city lights 50 miles south, something else. But here's where it gets stranger. What they had spent months trying to scrub out of their data was the discovery itself. The signal was the cosmic microwave background, the faint, cold afterglow left over from the Big Bang, and no amount of cleaning was ever going to remove it, because it was not coming from the antenna, or the pigeons, or the city. It was coming from everywhere at once. This light had been traveling freely since the universe was about 380,000 years old, the moment it first cooled enough to let light move through it without being scattered every few inches by a dense fog of charged particles. Before that moment, the universe was opaque, a glowing haze no telescope could ever see through. After it, light was finally free to travel, and some of that very first light is what Penzias and Wilson picked up, still arriving 13.8 billion years later, the entire age of the universe so far. Along the way, it cooled the whole distance down, from a fireball of billions of degrees to a faint whisper of microwave radiation. So faint it reads on an antenna as nothing more than background static. It fills every cubic meter of space that exists, not just near this antenna in New Jersey, but everywhere, arriving equally from every direction, which is exactly why Penzias and Wilson could never point their way around it. There was no clean patch of sky to check against, no control measurement without it. The hiss was the sky itself. That whisper has a temperature, 2.725 Kelvin. In more familiar units, about 454.8 degrees Fahrenheit, or 270.4 degrees Celsius. This is the baseline, not the temperature of a planet, or a nebula, or some especially dark patch of sky between the stars, but the resting temperature of the entire universe. Everywhere, all at once, in every direction anyone has ever pointed an instrument. It is not absolute zero, but on a cosmic scale, nothing natural has come closer, and for the rest of this story, that single number keeps returning, because it turns out to touch almost everything cold. Think about what that means for a moment. Every star, every comet, every drifting cloud of interstellar dust sits inside a faint bath of ancient light, gently holding it above absolute zero, whether anything else is nearby or not. There is no coordinate in the observable universe cold enough to escape it, no gap dark enough to hide from it, no silence total enough to sit outside its reach. The hiss that annoyed two men in New Jersey for months turns out to be the quiet flaw underneath everything else this story will describe, and it keeps falling. As the universe expands, that ancient light stretches into longer and longer wavelengths, thinning and cooling as it travels. Billions of years from now, it will sit closer to absolute zero than it does tonight, a fraction of a degree at a time, forever. The universe is not simply cold, it is still cooling, moving along a one-way path toward a stillness physicists have a name for: heat death, the point where every gradient finally equalizes, where nothing is warmer than anything else, and nothing is left to drive any change at all. That point is a long way off, farther than the number 13.8 billion can easily hold in the mind, and there is a great deal more to understand about it before it means much. It will come back later in this story, once the rest of the picture is in place. For now, what matters is smaller and stranger than heat death. Two men spent months trying to make an unwanted sound disappear, and the sound turned out to be the oldest light in existence, still arriving, still cooling, filling the space between every star before it ever reaches one. The direction was set the moment Penzias and Wilson stopped trying to explain the hiss away and started listening to what it actually was. They had gone looking for a flaw in their instrument and found the temperature of the universe instead. And 2.725 Kelvin, the number that would come to anchor nearly everything that follows, would turn out to be stranger than it first appeared. Stranger, yes, but only because the number gets used before anyone stops to ask what it is actually measuring. 2.725. Kelvin sounds precise, almost official, the kind of figure you accept and move past without a second thought. It deserves a slower look. Temperature is not a substance. It does not fill an object the way water fills a glass or air fills a room. It is a description, a measurement of how fast the particles inside something are moving, vibrating, colliding into each other. Hot means fast, cold means slow. That is the whole of it, however grand the physics built on top of it becomes. In boiling water, the molecules move at hundreds of meters per second, faster than a jet cruising at altitude, and they collide with each other billions of times every second. Cool that same water down to the inside of a kitchen freezer, somewhere around 18 degrees below 0 Celsius, and the molecules slow enough to lock into a rigid lattice, ice, but they do not stop. Even frozen solid, the atoms keep vibrating in place, jostling against their neighbors in a structure that never quite goes still. Nothing made of matter is ever perfectly quiet. The colder something becomes, the slower its particles move. Follow that trend down far enough, and there is a limit. A point where particles would carry no thermal motion left to lose. No vibration, no jostling, no heat left to give away. Physicists call it absolute zero. 0 Kelvin, minus 459.67 degrees Fahrenheit, minus 273.15 Celsius. Absolute zero is not simply the coldest temperature anyone has ever measured in a lab. It is the coldest temperature that can exist anywhere, under any conditions, for any reason. Below it, there is nothing left to measure. Temperature itself runs out of meaning. Set the universe's baseline next to that floor, and the distance nearly disappears. 2.725. Kelvin sits less than 3 degrees above absolute zero. For comparison, liquid water, the only form in which every living thing on Earth carries out its chemistry, exists across a span of 100 degrees Celsius. The entire resting temperature of the cosmos fits inside a gap more than 30 times narrower than the range water tolerates on this one ordinary planet. Here is a question worth sitting with for a moment. If the background radiation of the universe already sits that close to the floor, is it the coldest thing out there? It is not. Because the cosmic microwave background fills every cubic meter of space, any object sitting in that space absorbs a sliver of it, constantly, from every direction at once. That faint absorption warms the object just slightly above absolute zero, settling it near 2.7 Kelvin rather than at the floor itself. The number that sounded like the edge of nothing turns out to be the thing quietly keeping the rest of the universe from touching that edge. Not the coldest point in existence, the warmth that everything else in the cosmos leans on, however faint that warmth actually is. Somewhere else, colder places exist anyway. Dense clouds of gas and dust, scattered through the galaxy, can shield their own interiors from even that faint background. The way a thick blanket keeps a small patch of skin warmer than the room around it, except here the trick runs backward. Inside the thickest of these clouds, temperatures fall as low as 1 Kelvin. One object holds the record outright. The Boomerang Nebula, a young planetary nebula about 5,000 light-years away, near enough by galactic standards that its light left before human civilization began, has been measured at 1 Kelvin, 1 degree above the floor of everything, colder than the void around it, colder than the light that fills that void. The mechanism is not shielding alone. A dying star at the nebula's center is throwing its outer layers outward at enormous speed, and expanding gas cools as it expands, the same principle behind the chill of an aerosol can as the gas rushes out of the nozzle. The molecules do work pushing outward, spending their own energy to make room for themselves, and that spent energy comes straight out of their temperature. The outward rush has driven the nebula's gas below the resting temperature of the universe itself, making it, for now, the coldest known natural object anyone has found anywhere in the observable cosmos. So the number that anchors this story is not the floor, and it is not even the coldest thing space has managed to produce. It is a threshold, a resting point, worth remembering less for what it forbids than for what it quietly makes possible. Everything measured against it from here forward, the instruments built to study the faintest light in the universe, the human body dropped into vacuum, the slow machinery of survival, out where the sun is only a bright star, will be measured against a floor that turns out to have neighbors even colder than itself. Reaching them, or seeing anything that faint at all, will take instruments willing to grow almost as cold as what they are trying to find. To even detect something that cold, we have to get almost that cold ourselves. Or rather, our instruments do. The detectors behind the coldest astronomy, the ones that map the cosmic microwave background, that study the earliest galaxies, that catch stars still gathering themselves out of gas and dust, are built to register a single photon of infrared light. That is a sensitivity almost impossible to picture. One particle of light, arriving after traveling for billions of years, and the instrument notices it. But sensitivity like that comes with a cost. Any warm object glows in the infrared, not just stars and planets. The telescope itself, the housing around the detector, the wiring behind it, the mirrors, even the bolts holding the structure together. Everything above absolute zero radiates, a fact this whole story keeps circling back to, and a telescope is no exception. If those parts are warm, they flood the detector with their own light, drowning out the faint signal it was built to catch, the way a floodlight aimed at a telescope would drown out a distant star. An instrument sensitive enough to register a single photon from the edge of the universe is also sensitive enough to be blinded by its own electronics. So the detector has to be cooled until its own glow goes quiet, not dimmed, silenced, cooled far enough that the instrument stops being a light source and becomes only a listener. A telescope built to see the faintest things in existence has to first make sure it is not, itself, part of what it is seeing. The James Webb Space Telescope, launched on December 25th, 2021, is built around exactly that problem. Its near-infrared camera and spectrographs run at about 7 Kelvin, roughly 447 degrees Fahrenheit below zero. Some of its mid-infrared detectors run colder still. That is not a temperature anything alive brushes up against. That is a temperature engineered on purpose, layer by layer, at a cost of years and billions of dollars. It starts with where the telescope sits. Webb orbits the Sun from the second Lagrange point, about 1 million miles from Earth, positioned so the Sun, Earth, and Moon all fall on one side of the sky, leaving the other side facing permanently outward into darkness. Behind it trails a sunshield the size of a tennis court, 5 layers of a thin material called Captain, each one coated in reflective aluminum and silicon. Each layer blocks most of what little heat gets past the one before it, so the shielding compounds instead of simply adding up. On the side facing the Sun, that shield reaches roughly 230 degrees Fahrenheit, hot enough to soften plastic. On the telescope side, roughly 394 degrees below zero, a swing of more than 600 degrees across 5 sheets, no thicker than foil, held apart by nothing but empty space and careful engineering. That gets the telescope cold. It does not get it cold enough. A separate machine, a cryocooler, actively pumps heat away from the coldest instruments. The same basic principle as a refrigerator, just working far harder, toward a far lower target, running continuously, so the detectors never drift back up toward the noise they were built to escape. Put the sunshield, the orbit, and the cryocooler together, and Webb becomes, in a practical sense, the coldest instrument humans have ever put into space. Not the largest, not the most expensive line by line, the coldest, and that turns out to be the thing that mattered most. Here is the strange part. Webb is cold because the universe it is looking at is cold. Light from the earliest galaxies left its source more than 13 billion years ago, and the expansion of the universe has stretched that light on its way here, sliding it out of the visible spectrum and into the infrared. Reading the faint infrared afterglow of a hot young universe means building an instrument that adds no infrared of its own. The telescope's cold is not incidental to the science. It is the price of the science. The universe speaks in faint whispers, and those whispers are only heard in the cold. Not bigger mirrors, not sharper optics. Cold, first and always. None of this needs a launch pad. Some of the sharpest measurements of the cosmic microwave background have come from the ground, from a 10-meter microwave telescope planted at the South Pole, roughly 9,300 feet up on the Antarctic ice. The reason is not just that the site is remote and quiet, though it is both. Water vapor absorbs microwave light before it ever reaches a detector, the same way fog blurs a distant view and air cold enough to freeze most of the moisture out of it stops absorbing. The South Pole is so cold that its air holds almost no water at all, which leaves it nearly transparent to the very wavelengths the telescope is built to catch. A warmer, wetter site could carry the same telescope and still miss the signal, buried under microwaves the sky itself gave off. So the cold at the bottom of the world is not incidental either. It is doing the same job the sunshield does 1 million miles away, clearing the air of anything that might drown out a signal that has traveled since nearly the beginning of time. Cold, it turns out, is not only the thing astronomers study, it is the condition that makes studying anything at all possible. Whether the instrument is drifting 1 million miles from Earth, or bolted to the ice at the bottom of the world. And if reaching the coldest signals in the universe takes instruments built to rival deep space itself, the emptiness those instruments stare into might not be as simple as it looks. Point one of those frozen instruments at the emptiest patch of sky you can find, farther from any galaxy, any star, any planet, past every last wisp of gas or dust, and you would expect to be looking at pure nothing. You are not. Physicists have a name for what is actually there, something most people have never heard of, a phenomenon called the Casimir effect. Quantum mechanics does not allow a truly empty vacuum. Even a perfect vacuum, one with exactly zero particles floating inside it, is filled with what physicists call vacuum energy, or zero-point fluctuations. The value of a physical field can never sit at exactly zero everywhere, not even in the depths between galaxy clusters, not even in a box built to hold nothing at all. The electromagnetic field trembles randomly instead, throwing off waves of every wavelength, flickering into existence and out again, almost as soon as they appear. These flickers have a name too: virtual photons. Not permanent particles, gone as soon as they arrive, but real enough to leave a trace on anything nearby. In 1948, a Dutch physicist named Hendrik Casimir worked out what that trembling would do if you gave it a wall to push against. Take two plain metal plates, uncharged, and bring them close together in a vacuum, closer than the width of a human hair. Between them, the fluctuating field gets restricted. Think of a guitar string stretched between two fixed points. Only certain wavelengths fit neatly between the ends, the ones that settle into a whole number of waves. The rest cannot form at all. They are simply forbidden by the geometry. The gap between Casimir's plates works the same way. Wavelengths longer than the gap cannot fit inside it, while outside the plates, in the open space around them, every wavelength still flickers freely, with nothing narrowing the choices. That mismatch matters. Fewer wavelengths fit inside the gap than outside it, so there is less vacuum energy pressing outward from between the plates than there is pressing inward from around them. The imbalance is small, but it is not zero. The plates get shoved toward each other by the vacuum itself. Casimir predicted the size of that push in 1948, working it out purely on paper, with no way yet to test it. Nobody measured it convincingly for almost 50 years. In 1997, an experiment finally caught the force directly, and the number matched Casimir's prediction with striking precision. Not a rounding error, not a coincidence, a real, measurable push, coming from nothing, landing almost exactly where the equations, worked out on paper decades earlier, said it would. This is not some sealed-away laboratory curiosity either. Engineers building machines at the nanometer scale, the tiny mirrors and switches inside modern electronics, run into the Casimir force constantly. Components stick together for no obvious reason, welded shut by a force too small to notice at any ordinary size, until someone remembers that the vacuum between them was never truly still. Design a machine small enough, and the emptiness itself becomes part of the engineering problem, and the effect points at something far larger than nanotechnology. The cold vacuum of space, the same emptiness those frozen telescopes stare into, is not nothing. It seethes. Virtual particles flicker in and out by the moment. Vacuum energy trembles continuously, and this is true everywhere, even in the coldest, loneliest gaps between galaxy clusters, light years from the nearest star, far past anywhere a telescope's own warmth could ever reach to interfere. But here's where it gets strange. Those fluctuations carry real energy, and physicists have wondered for decades whether the total energy of all that vacuum trembling, summed across the entire universe, might be the very thing driving the universe apart. Dark energy, the mysterious pressure behind the accelerating expansion of everything, has never been explained. Vacuum energy looked for a while like the answer sitting in plain sight. Could the same trembling that shoves two metal plates together also be pushing entire galaxies farther apart? It was a tempting thought. It is not that simple, or at least not yet. Add up the vacuum energy the equations predict, compare it to the dark energy actually observed, and the two numbers refuse to agree. Not by a little, by an enormous margin, one so large that physicists sometimes call it the worst prediction in all of physics. Whatever is pushing the universe apart, it is not simply the vacuum energy Casimir's plates revealed, or not in any straightforward way anyone has worked out yet. We don't fully understand the connection, but the suggestion will not quite go away either. The cold, empty void has energy. It has structure, and in some sense nobody has pinned down yet. That restless quantum trembling may be tangled up with the very force stretching space apart, holding a piece of an answer that still will not resolve. Scientists keep returning to the discrepancy anyway, because a measurable force between two metal plates is hard evidence that the vacuum is not simply nothing, and hard evidence is rare in a question this large. The cold of space, it turns out, is not passive. Even in perfect emptiness, even at temperatures within a whisper of absolute zero, something is happening, ceaselessly, in every cubic meter of the darkest void, whether anyone is there to measure it or not. No telescope needs to point at it. No detector needs to be cooled to catch it. It is simply there, running underneath everything else this story has described. And whatever is happening out in that trembling dark, it will matter again once this story turns from the vacuum itself to a single human body, dropped into that same emptiness, with nothing standing between it and the void at all. Place that single body in the trembling dark, and the emptiness stops being an abstraction. It becomes a question about survival, one your body is quietly answering every second of your life, warm or cold, awake or asleep. You are a thermal system before you are anything else. Metabolism burns fuel constantly, releasing heat at roughly the output of a 100-watt light bulb left on all day, and every second some of that heat drains away again, through conduction against your chair, through convection in the air moving across your skin, through radiation leaving your surface as infrared light. The whole arrangement exists to hold your core somewhere between 94 and 107 degrees Fahrenheit, 34 to 42 degrees Celsius, a window not much wider than the difference between a cool spring afternoon and the water drawn for a hot bath. That window is smaller than it sounds. Drop below 94 degrees and the mind goes first. Judgment slips before the shivering does. Cold, confused people have been found partly undressed in freezing conditions, having somehow decided, in their last clear moments, that they were too warm. A paradox rescue workers have learned to expect and dread. Coordination fails next, hands fumbling zippers and buttons they could manage moments earlier. Shivering, the body's own furnace turns violent, then stops. The muscles too exhausted to keep burning fuel. Near 82 degrees, the heart begins to skip and stutter. Near 78 degrees, it can stop outright. Climb too high instead, and the failure looks different but arrives just as fast. Past 107 degrees, proteins begin to unfold, losing the folded shape that lets them do their work at all. Enzymes stop working. Cells start to die, and the brain, more sensitive than almost any other tissue, can take permanent damage within minutes. 13 degrees Fahrenheit, about 7 Celsius, separates the low collapse from the high one. Against a universe that ranges from billions of degrees inside a newborn neutron star to 2.725 Kelvin in the depths between galaxies, that gap is an infinitely thin sliver. Holding it takes constant, active work, a furnace, a radiator, and a thermostat, all built from the same fragile chemistry, and the moment that work stops, the sliver closes fast. So what actually happens if you cross into that trembling dark unprotected? Wait, not what the instinct says. You would not freeze solid. You would not shatter like a dropped glass. The near vacuum of space is of all things an excellent insulator, with almost no matter left to carry heat away from your skin. So radiative cooling alone is slow, far slower than the danger that actually kills first. Something faster gets there before the cold ever does. Gas dissolved in your blood would come out of solution within seconds. The way a shaken soda foams the instant the cap comes off, except now inside living tissue in the vessels that feed the brain and heart. Moisture on your eyes and in your airway would boil away into vapor despite the cold, because pressure, not temperature, decides when water turns to gas, and out there pressure is close to nothing at all. Air would rush out of your lungs in one uncontrollable breath. Starved of oxygen, you would lose consciousness in about 15 seconds, roughly one unhurried breath, and brain death would follow within minutes. The cold, for all its reputation, would not even be the thing that reached you first. After that, the body left behind cools slowly, by radiation alone. In direct sunlight, in orbit, it might absorb more warmth than it sheds, and stay dangerously warm rather than freeze. In shadow, wrapped in its own stubborn insulation, it might take an hour or longer to cool significantly. Not a quick freeze, a long, patient drain measured in hours, not seconds. Spacecraft face a gentler version of the same arithmetic every day, and they face it constantly, not just at the edge of survival. Engineers do not design against one dramatic freeze. They design against a running heat budget, tracking how many watts each component generates, how many it radiates away, how many pass by conduction into the structure around it, recalculated again and again across a single orbit, a single day, an entire mission. Get the budget wrong in either direction, too hot or too cold, and electronics fail just as surely as a body would. Not every failure looks the same. The Mars Climate Orbiter was lost in 1999 to a navigation error, not a thermal one, but heat and cold have claimed instruments on other missions just as completely. In 1995, the Galileo probe plunged directly into Jupiter's atmosphere, built to survive one of the most punishing thermal environments in the solar system, and transmitted data for 57 minutes, barely longer than a lunch hour, before the heat and pressure below the visible clouds crushed and melted it completely. 57 minutes was the entire budget it had. Farther out, the challenge flips entirely. Beyond about 5 astronomical units, 5 times the distance separating Earth from the Sun, sunlight grows too faint to power anything useful, and it only grows fainter with every year of travel outward. Solar panels stop being an option, no matter how wide you build them. Voyager, Cassini, and New Horizons carry radioisotope thermoelectric generators instead. RTGs, blocks of plutonium-238 weighing no more than a couple of bowling balls, decaying slowly and steadily for decades without any moving parts to wear out. That decay throws off heat the way a tiny nuclear campfire would, warming instruments that would otherwise slip below their operating range in a night that never ends and never brightens. Past 5 astronomical units, staying warm is not a passive fact of sitting near a star. It has to be built, fed, and carried along, one slowly decaying nucleus at a time, for as long as the mission needs to keep breathing. The same cold that would take an unprotected body by inches and a spacecraft by fractions of a degree each orbit was never as simple a number as it first seemed either. That number, 2.725 Kelvin, sounds like a single settled fact, fixed everywhere at once. It is not. Temperature is not a property that space carries the way a room carries a paint color. It is a description of matter, of particles moving, vibrating, colliding into one another, and trading energy as they go. In a gas, temperature is the average speed of billions of molecules banging around inside a container. In a solid, it is how hard the atoms shake while held in place. Both descriptions depend on matter having neighbors close enough to strike. Interstellar space famously holds about 1 atom in every cubic meter. Those atoms are not still. Some regions of that thin gas run hot, not gently hot, but thousands of degrees hot, in places tens of thousands of Kelvin, judged by how fast the individual atoms move. And the same patch of sky, described by its background radiation, sits at 2.725 Kelvin, a hair above the coldest anything can be. How can the same patch of sky be sweltering and freezing at the same time? Both readings are true at once. Something else was happening. An atom moving at 10,000 Kelvin, alone in a room-sized volume, almost never meets another atom to hand that energy to. 1 atom per cubic meter means real collisions are rare, spaced out over long stretches of time and distance. The energy is genuine. It is simply locked inside a single particle with nothing nearby to receive it. Not cold, not hot, isolated. Bring a thermometer close enough to touch one of those fast atoms, and almost nothing would happen. A thermometer works by letting particles collide with it until both sides settle at the same speed, the same jostle. With only 1 atom to strike it every so often, the thermometer would spend years waiting for enough collisions to register anything at all. Long before that, the surrounding light, not the scattered atoms, would already have set its reading. The thermometer would report the radiation's temperature, 2.725 Kelvin, and never once notice the furnace of fast-moving atoms drifting past it in between. This is the point where the number driving this whole story needs a correction. When physicists say the temperature of space is 2.725 Kelvin, they are not describing the scattered atoms at all. They mean the radiation field, the ancient microwave light left over from the birth of the universe, filling every direction in equal measure. Drop an object into that field and give it enough time, and it settles at 2.725 Kelvin, not because a handful of distant atoms warmed it, but because the light did. Out here, temperature turns out to be a property of the light passing through, not of the near nothing carrying it. Even that settling takes longer than instinct expects. Radiation is the slowest way heat travels, and in a vacuum, it is the only way available. A bright, reflective object drifting far from any star does not snap to 2.725 Kelvin the moment it arrives. It cools or warms at its own unhurried pace, over hours, sometimes over days, depending on what it is made of and how its surface is finished. An object in space is cut off from its surroundings in a way nothing on the ground ever is. Consider the same structure the last section left, running its heat budget, only now seen whole. One face of a spacecraft in orbit points toward the sun. The other points away, into the dark. The sunlit face climbs to roughly 250 degrees Fahrenheit, hot enough to blister skin on contact. The shadowed face, at that same instant, drops to roughly negative 250 degrees, cold enough to damage exposed flesh in seconds. 500 degrees of difference on one structure at one moment, separated by nothing thicker than a wall of metal and insulation. Not a single temperature. Two, at once, inches apart. The cause is not that space runs hot in one direction and cold in the other as some general rule. It is that radiation only travels in straight lines, and nothing in a vacuum carries heat around a curve to blend the two sides. There is no wind to mix them, no shared air to average them out. Whatever faces the sun bakes. Whatever faces away freezes. The vacuum sits between them like a wall heat cannot cross. Holding a structure together across that swing takes constant, active work, not a passive shrug at the extremes. The International Space Station unfolds large radiator panels built to shed heat into the dark side of the sky, wraps its delicate instruments in multiple layers of insulating blanket, and runs loops of liquid ammonia between hot components and those same radiators, carrying heat the way a car's cooling system carries it away from an engine, by moving fluid rather than waiting on conduction alone. Heaters switch on for anything left in shadow long enough to fall toward failure. Spacesuits carry the identical logic at a smaller scale. Beneath the fabric, a spacewalking astronaut wears fine tubing circulating water against the skin, hauling metabolic heat away in direct sunlight, and holding it close when the suit swings into shadow. Fans keep air moving so the visor does not fog. The suit is less a garment than a small personal spacecraft, doing continuously and invisibly what the whole station does at a larger scale. Take any of it away, even briefly, and the same body that manages its own 13-degree window without thinking would be overwhelmed within minutes by a swing measured in hundreds. Cold, out here, does not kill with a single number. It kills with the extremes, and with the total absence of anything willing to blend one into the other. None of it equalizes on its own. That is the deeper point sitting underneath the engineering. On Earth, air and water and ground are always quietly averaging every temperature difference back toward the middle, which is why a room feels like one temperature and not 50. Remove the air and the water and the ground, and averaging stops happening. Every surface is left to negotiate its own temperature directly with whatever light happens to be striking it, with nothing else nearby to argue it back toward the middle. A structure built to survive that swing was only ever solving half the problem. The harder lesson was waiting in the metal itself, in what cold does to a material long after the temperature has stopped being the interesting part. Hold a structure across a divide like that for long enough, and the more interesting question stops being which side is hotter. It becomes what the metal underneath has quietly turned into. At room temperature, somewhere around 70 degrees Fahrenheit, 21 degrees Celsius, about as warm as a spring afternoon with the windows cracked open, a piece of steel looks and feels like a fixed, solid thing. It is not standing still. Its atoms vibrate constantly in place, and its electrons wander freely between them. The same looseness that lets a metal pan carry heat from a stove into your palm and lets a copper wire carry a current through a wall. That freedom of movement gives the metal room to bend. Stress it, and its atoms shift and slide past one another instead of snapping apart. Hammer it, roll it, draw it thin enough to wind into wire, and it gives, gradually with warning, long before it fails. This is ductility. Warm metal has it in abundance. Cool that same steel, and the freedom drains out of it. The vibration that let atoms slip past each other slows. The crystal lattice locks into something closer to rigid. The atoms held in fixed positions instead of a loose, forgiving crowd. Stress cold metal the same way, and it does not bend first and warn you. It shatters, clean fractures, sudden, no warning, no bending first. Metallurgists call this the ductile to brittle transition, and engineers now design around it deliberately, choosing alloys and coatings that resist it in cold climates, in aircraft, in pipelines, in anything meant to survive a winter. That caution exists because the transition has ended machines, wrecked pipelines, and once helped sink the largest ship ever built. On the night of April 14, 1912, the water of the North Atlantic sat at roughly 28 degrees Fahrenheit, about 4 degrees below the point where fresh water freezes, cold enough to numb bare skin within minutes. Metallurgists who later examined steel, recovered from the Titanic's hull, found something the shipbuilders never measured. The steel carried an unusually high sulfur content, and sulfur-heavy steel turns brittle at exactly the kind of cold that ocean held that night. When the hull struck the iceberg, the plating did not dent and buckle the way modern steel would. It cracked. It separated along its seams like a dropped ceramic plate, opening thin gaps at the rivets and seams that a more forgiving steel would simply have bent around. Not a slow bending failure, a shattering one, and it let the sea in far faster than warmer, more forgiving steel ever would have. The cold did not cause the disaster. It changed what the hull was made of, in every way that mattered once the iceberg was already there. Push past a ship's hull and out toward the temperatures of deep space, brushing close to 450 degrees Fahrenheit below zero, 268 degrees Celsius below zero, only about 9 degrees above the absolute floor where all thermal motion stops. And the same transformation stops being occasional. Not occasional anymore, total. Metal parts embrittle completely, down to the smallest bracket and bolt. Rubber seals, which depend entirely on flexibility to hold a joint airtight around a hatch or a fuel line, turn hard and crack apart like fired pottery, and a cracked seal in a pressurized spacecraft is not a minor fault. Oils and lubricants that keep machinery sliding smoothly on Earth thicken, then stop flowing altogether, effectively solid. So moving parts that once slid freely can simply seize. And it does not stop with rubber and steel. Gases behave the same way. Nitrogen makes up most of the air moving in and out of your lungs right now, so stable at room temperature that factories use it just to keep sensitive equipment from reacting with anything at all. Cool it down and that stability disappears fast. Around negative 320 degrees Fahrenheit, nearly 196 below 0 Celsius, nitrogen turns liquid, cold enough that dipping an ordinary rubber ball into it and tapping the ball against a table will shatter it like glass. Cool it further, past negative 346 Fahrenheit, 210 below 0 Celsius, and it freezes solid. Farther out in the solar system, that is simply the weather. Methane and carbon dioxide, gases here, freeze into ice out there. Pluto's surface carries patches of frozen nitrogen, frozen methane, and frozen carbon monoxide, laid out across its plains and craters like geology, not like weather at all. Substances we breathe, or smell, or measure as vapor drifting off a container, exist there as rock, solid enough to hold a mountain shape. This is why spacecraft built for the outer solar system carry heaters as standard equipment, not an afterthought bolted on later. Engineers plan for it from the first design sketch, running heater lines beside every sensitive component the way a house runs wiring beside its plumbing. The Voyager probes, launched in 1977 and now adrift in interstellar space, still run small heaters specifically to keep their electronics from crossing into that same brittle, frozen territory. Without them, the cold would not just slow the instruments down, it would change what their components are, the same way it changed a ship's steel, a seal, a block of frozen air. Cold, it turns out, does not just make familiar things colder versions of themselves. It reaches into what they are made of and rewrites the answer. Metal stops bending and starts shattering. Rubber stops flexing and starts cracking. Air itself stops being air and becomes ground solid enough to stand on. None of these substances change their chemical identity to do it. Steel is still steel, nitrogen is still nitrogen, atom for atom. What changed is behavior. How each one responds when something pushes against it. And behavior turns out to matter just as much as identity does. Engineers who design for the outer solar system now treat this as a first principle rather than a surprise. Every seal, every fastener, every drop of lubricant gets tested at temperatures most materials never see on Earth. Because a spacecraft that works perfectly at room temperature can fail completely once it drifts far enough from the sun. The lesson the Titanic taught by accident in one cold ocean on one night is now designed around, on purpose, mission after mission, world after world. The next question is whether that same cold reaches even further into the chemistry that builds and sometimes preserves life itself. That reach starts with a plain fact. All chemistry runs on temperature. A reaction happens when two molecules collide hard enough to break old bonds and form new ones. And how often that collision carries enough energy depends entirely on how warm or cold the surroundings are. Warm something and molecules move faster, collide harder, react more often. Cool it down and they slow. Cool it far enough and the reactions stop. This is true of a pot of water on a stove, true of milk, souring on a counter, true of a battery losing its charge in the cold. It is also true of the body. Life is chemistry. Nothing more mysterious than that. Breathing, digesting, thinking, healing, every signal that fires along a nerve, all of it is a cascade of chemical reactions running at a pace set by tissue temperature. That is why the body holds so tightly to about 98.6 degrees Fahrenheit, 37 degrees Celsius. The number A thermometer is built to expect when nothing is wrong. The enzymes and proteins carrying out those reactions only work efficiently inside a narrow band around that point. Drop the body's core below it and metabolism slows. Heart rate slows, breathing slows, thinking slows. Somewhere near 86 degrees Fahrenheit, 30 degrees Celsius core, a drop of only about 12 degrees, roughly the difference between a warm bath and one already going cold, the reactions of life effectively stop. Not violence, not trauma, just chemistry, slowing to a stop. That is what cold kills through, far more often than not. A quiet subtraction, not an attack. We don't often think of dying of cold as a chemistry problem, but that is exactly what it is. A body's own reactions running down like a clock left unwound. By that logic, the coldest reaches of space, the dark clouds of gas and dust drifting between stars at close to 1 Kelvin, should be about as chemically dead as anywhere gets. Molecules there barely move. They do not collide hard enough to break a bond or form one. Ordinary chemistry, the kind that runs a human body or a kitchen stove, has nowhere near enough energy to proceed. Every model built on ordinary collision chemistry says the same thing, that a cloud this cold should sit chemically frozen, inert, going nowhere for as long as it exists. So how, in cold that absolute, could anything build at all? But here's where it gets strange. Something does happen there, just not through collision. Those slow molecules still drift, and they still settle, landing on the surfaces of dust grains scattered through the cloud, particles of silicate and carbon roughly 1/1,000,000th of a meter across, no larger than the specks that make wood smoke visible in a shaft of light. Molecule by molecule, over millions of years, ice accumulates on those grains in layers. Water ice first, then carbon monoxide, carbon dioxide, methanol, ammonia, a frost building up one atom at a time in the dark. And on the surface of that frost, something takes over that has nothing to do with heat at all. Quantum mechanics. Ordinarily, a reaction needs enough energy to climb over a barrier, forcing old bonds apart before new ones can form. The way a ball needs enough of a push to crest a hill before it can roll down the far side. Quantum tunneling does not climb the hill. It passes through it, as if the ball simply appeared on the other side without ever reaching the top. The odds of that shrink fast as the barrier grows taller, but for the lightest atoms, hydrogen most of all, the odds stay just high enough. Tunneling keeps working long after ordinary chemistry has given up, one reaction at a time, across spans of years no laboratory on Earth could ever wait out. No spark starts it, no collision drives it, just cold, patience, and a rule of physics that lets particles cheat. The molecules astronomers have found built this way are not simple. Methanol, ethanol, formaldehyde, glycolaldehyde, a simple sugar, acetaldehyde, dimethyl ether, formic acid, all of them assembled, atom by atom, on grains of frozen dust, colder than almost anywhere else in the universe. And in material blasted off comets, fragments of that same cold ancient ice, scientists have detected glycine, one of the 20 amino acids that build every protein in every living thing on Earth. It has sat preserved in that frozen state for some 4.5 billion years, nearly the entire lifetime of the Sun and the planets that orbit it. It most likely formed the same way, through slow tunneling chemistry on a grain of dust in the cold cloud that came before our solar system existed at all. No one has caught that exact reaction happening, not directly. The timescale is too long and the setting too remote for any experiment to watch it unfold from start to finish. What sits in laboratories today is the finished molecule, pulled from ancient ice, carrying every sign of having been built exactly this way. So the cold of space is not a dead silence after all. It is a slow, patient, quantum mechanical chemistry laboratory, running its reactions over millions of years instead of milliseconds, with no flame and no collision, nothing but frozen dust and time. Its finished products, complex organic molecules riding on grains of ice, get folded into new stars and new planets when the cloud holding them finally collapses under its own gravity. It remains a strong likelihood rather than a settled fact, but the ingredients that made life possible on Earth may never have needed stellar heat at all. They may have been assembled patiently, out between the stars, long before there was a sun to warm anything. Not just a barrier then, a cradle as well, standing quietly in the dark, far from any star, and the reach of that cold does not end there. The cold that builds those molecules sits far out, between the stars, patient and slow, with nothing but time to work with. Closer to home, in the neighborhood we actually live in, cold and heat trade places from world to world, in ways the simple rule, closer to the sun means hotter, cannot explain. Read the numbers straight through, from the sun itself to the edge of its reach, and the failure of that rule becomes its own kind of tour. Start at the source. The sun's visible surface, the photosphere, sits at roughly 9,140 degrees Fahrenheit, hotter than any furnace built on Earth, hot enough to vaporize steel on approach. Above that surface, the sun's outer atmosphere, the corona, visible only during a total eclipse as a pale halo, reaches several million degrees Fahrenheit. Heat is supposed to flow from hot to cold, cooling as it moves outward from its source. So why does the layer farthest from the sun's core burn hotter than the layer beneath it? It should not. Not slightly hotter, thousands of times hotter. And after decades of research and a string of dedicated spacecraft built solely to study it, no one fully understands why. The mechanism remains a genuine open question, one of the few unsolved mysteries sitting in plain sight, on the surface of the nearest star we have. Move outward, and the simple rule holds for exactly one planet before it starts breaking. Mercury has almost no atmosphere to hold heat, or carry it from one side to the other, so it swings harder than anywhere else in the solar system. Its sunlit face reaches about 800 degrees Fahrenheit, hot enough to melt lead. Its dark face drops to nearly 290 degrees below zero, cold enough to stop most metals from bending at all. One slow rotation, 59 Earth days, carries the same rock across more than 1,000 degrees. Venus sits farther from the sun than Mercury and should, by that logic, run cooler. It does not. Its atmosphere, a thick blanket of carbon dioxide, lets sunlight in and will not let the heat back out. A greenhouse with no exit. Surface temperatures reach 860 degrees Fahrenheit, hotter than Mercury at its worst, and it barely varies, day or night, pole or equator. Distance from the sun turned out to be the wrong question. Venus is proof that an atmosphere can matter more than an address. Earth's own average, 57 degrees Fahrenheit, sits gently between those extremes, comfortable enough for water to stay liquid and chemistry to keep running. But an average hides a great deal. At Vostok Station in Antarctica, in July of 1983, the air dropped to almost 129 degrees below zero, cold enough to make exposed metal brittle within seconds and dangerous to breathe unprotected. A reminder that even Earth carries a sliver of the same physics found in the far colder places this story keeps returning to. In Death Valley, the same planet has recorded 130 degrees above zero, hot enough to fry an egg on the open ground. One world, one average, and a swing of more than 250 degrees between its own extremes. Mars runs colder throughout, averaging about 80 below, but even Mars keeps a kind of day-night violence. Near the equator in summer, the ground can briefly warm past 70 degrees Fahrenheit by early afternoon, then collapse to roughly 100 below by midnight. At its poles in winter, the air falls to nearly 195 degrees below zero. Cold enough that carbon dioxide, the very gas we breathe out, freezes directly out of the thin atmosphere and settles onto the ground as dry ice. Something we exhale without a thought becomes solid ground on another planet. Farther out, the numbers stop behaving at all. Jupiter's cloud tops sit near 230 degrees below zero, but bury a thermometer deep enough beneath that cold ceiling, and the story reverses completely. Crushed under its own enormous weight of gas, Jupiter's core is believed to reach roughly 43,000 degrees Fahrenheit, hotter than the visible surface of the Sun itself. Saturn's clouds sit near 288 below. Uranus, tilted onto its side, reads near 357 below. Neptune's cloud tops, at almost 393 degrees below zero, are the coldest planetary atmosphere anywhere in the solar system. And yet Neptune radiates about 2.5 times more energy than it receives from the Sun, warmth left over from its own formation 4.5 billion years ago, still leaking outward from the inside. The coldest atmosphere in the solar system sits on top of a planet that is, in its own quiet way, still warm. Then Pluto, drifting at an average of 3.7 billion miles from the Sun, roughly 40 times farther out than Earth, holds surface temperatures between 375 and 400 degrees below zero. When New Horizons flew past in July of 2015, it did not find the dead, featureless ball of ice most people expected. It found plains of nitrogen ice, mountains of water ice standing miles high, layers of methane haze, and hints of past geological motion. Not simple, not featureless. Alive in its own frozen way, with geography. Keep going. Past Pluto, past the last of the planets, and the Sun's influence itself finally gives out. At roughly 11 billion miles out, a gap so wide that light, which reaches us from the Sun in about 8 minutes, needs the better part of a day to cross it. The solar wind runs out and meets the true interstellar medium. This boundary is the heliopause, the edge Voyager 1 actually crossed. Beyond it, the background settles to the number we have already sat with, 2.725 Kelvin, the floor the whole universe leans against. Stand back from all of it, from the Sun's 9,140 degrees down to less than 3 degrees above absolute zero, at the edge of its own reach, and the solar system stops looking like a neighborhood of planets and starts looking like one small, fragile fact. A single star, burning fiercely enough to vaporize steel, sits at the center of an ocean of cold, and everything warm within reach of it. Every planet, every moon, every degree above absolute zero, borrows that warmth from one lone source surrounded on all sides by a universe that would rather be cold. And the worlds farthest from that light were about to prove stranger still. Pluto's plains and mountains were only the first warning. Farther out still, past the last of the officially numbered planets, the Sun does not simply fade. It changes what a world can be. Stand on any of these distant worlds and look up, and the Sun you would find there is barely a sun at all. A hard, bright point among the stars rather than a disk that warms a face. We picture the solar system as the Sun's lit, warm domain, and for the 4 inner planets that picture holds up well enough. It stops holding up the farther out you travel. Neptune sits roughly 2.8 billion miles from the Sun, close to 4.5 billion kilometers, something like 30 times the distance separating Earth from its own star. At that range, the Sun delivers about 900 times less energy per square meter of ground than it delivers here. Picture the brightness of a clear summer afternoon on Earth, then shrink it down to something closer to a single candle held a few feet from your face. That thin light is still enough to outshine a full moon back home, bright enough to walk by without stumbling. It is nowhere close to daylight. So is the outer solar system simply a colder version of the one we know? It is not. Without enough sunlight to drive it, the chemistry that shapes the inner planets slows to almost nothing out there. Gases that stay gas anywhere closer to the sun freeze out, settle as frost, then harden into something closer to rock than weather. Distance does what a deep freezer does at home, only slower and far more completely. Cold this deep does not just lower a number on a dial. It changes the category a world belongs to, and two moons, one circling Saturn and one circling Neptune, show just how far that change can go. Titan shows exactly what that difference produces. Saturn's largest moon carries a thick nitrogen atmosphere, denser at the ground than Earth's own air, and thick enough to hide the whole surface beneath a permanent orange haze. Under that haze lie lakes, not water, methane, ethane. The same simple hydrocarbons that burn as gas in a stove on Earth sit here as liquid, pooled in basins and fed by rivers, because the surface holds at roughly 290 degrees Fahrenheit, 79 Celsius, cold enough to keep methane liquid the way Earth's own temperature keeps water liquid. Titan even runs weather on that chemistry. Methane rain falls from hydrocarbon clouds. Methane rivers carve channels through icy bedrock. Methane deltas spread out where those rivers reach the shorelines of methane lakes. Windblown dunes ripple across dry stretches between them. A river, a delta, a coastline, a dune field. Every shape is one any geographer on Earth would recognize on sight, built from a substance Earth normally burns rather than sails on. The Cassini spacecraft, orbiting Saturn from 2004 to 2017, mapped this entire landscape by radar, since Titan's thick haze blocks any ordinary camera from ever reaching the ground. What Cassini found, patiently, orbit after orbit for 13 years, was Earth's familiar geography wearing none of Earth's familiar chemistry. Cold had not erased the shapes we know. It had simply rebuilt them out of something else entirely. Triton goes further still. Neptune's largest moon sits at roughly 391 degrees Fahrenheit, 235 Celsius, cold enough that nitrogen, the very gas that fills most of the air around you right now, lies frozen solid across its ground, near the coldest surface found anywhere in the solar system. By any reasonable expectation, a world that cold should be finished. Locked. Geologically silent. It is not. Triton has geysers. Not volcanic ones. Not molten rock forced up from a hot interior. Nitrogen geysers, and sunlight alone powers every one of them. Triton's surface is coated in nitrogen ice, clear the way window glass is clear, and that clarity is the whole mechanism. Faint sunlight passes straight through the ice and warms the darker material trapped just beneath it. That buried material heats just enough to turn solid nitrogen directly into gas, skipping the liquid stage entirely, and the pressurized gas breaks upward through the ice in plumes that carry dark dust several miles into Triton's thin atmosphere, high enough to be caught drifting downwind before it settles again. The sunlight driving all of it is fainter, at that distance, than the light from a single household LED bulb. A bulb dim enough to leave a room in shadow is, out there, enough to blast dust for miles into the sky. That is the real lesson these outer worlds are teaching. Cold does not mean stillness. It means matter balanced on the narrowest possible edge, solid and gas sitting so close together that almost nothing, sunlight too weak to read by, is enough to tip the balance and send gas breaking into open sky. On a warmer world, that same trickle of sunlight would vanish, lost in the noise of everything else already happening, drowned out by heat sources 1,000 times stronger. Out here, with nothing else competing, it is the whole story. The colder a world gets, the less it takes to move it, and the more that small input is left to do all the work alone. The solar system, all of it, The blazing sun and the 8 planets and every icy moon around them turns out to be only the warm room at the front of a much larger house. Every fact gathered on this tour, the corona's mystery, Venus's stolen heat, Neptune's leftover warmth, Titan's rivers, Triton's geysers, belongs to that one room. Beyond even Triton, past the last thin ring of ice, something colder waited. Colder and larger than any single world or any single room could ever be. Something colder waited beyond Triton, and it turns out to be almost everything. Step back far enough, past every planet, past the sun itself, past the whole crowded neighborhood of moons and rings and comets, and a different structure comes into view. Galaxies do not scatter evenly across the dark. They cluster into groups. Groups gather into larger clusters. Clusters link together along filaments, long thin streams of galaxies and gas stretching hundreds of millions of light years, a distance so vast that light setting out from one end, long before the first dinosaurs walked the ground, would still be crossing it today. Astronomers call the whole arrangement the cosmic web, and mapped out on a screen it looks almost organic, threads and knots and long empty gaps, less like a scatter of dust and more like a web an insect might spin, if it worked on the scale of galaxies instead of gardens. Between those filaments sit voids, vast regions where almost nothing lives. A single void can span hundreds of millions of light years across, and voids like this are not rare exceptions tucked into an otherwise busy universe. They make up most of it. Whatever thin gas drifts inside a void sits at a temperature close to the cosmic background, close to 2.725 Kelvin, though in the very largest voids that gas may run a touch warmer, faint radiation passing through and nudging it up by a fraction of a degree. That hedge does not change the larger picture. Fundamentally, a void is cold, empty, and dark. It stays that way, and it has stayed that way for longer than any star inside it has existed. We picture the universe as a glittering tapestry of galaxies, spiral arms and starlight scattered edge to edge, the kind of image printed on posters and hung on observatory walls. Is that the true picture? Picture instead the whole observable universe shrunk down to fit inside a single room in your house. The observable universe holds a volume of roughly 415 billion cubic light years, and 1 light year alone is about 5.9 trillion miles, a distance the mind cannot really hold on its own, let alone multiplied by hundreds of billions. Shrink all of it into that one room anyway, and go looking for the furniture. There is barely any. Every galaxy, every star, every planet, the whole glittering tapestry astronomers photograph and print on posters, would not fill a shelf in that room. Not most of the room. Not even most of the air inside it. Not a tapestry. An almost empty room, with a few scattered threads of light drifting through it. Dust motes catching a beam of sun in an otherwise bare house. That is the true face of the universe, and it is not the one in the photographs. The structure we celebrate, the clusters, the filaments, the whole cosmic web, occupies only a sliver of the total volume. The rest is void, cold, empty, near the floor of everything. Galaxies and stars are not the rule out here. They are the exception, and a rare one, and the cold void is the rule. Every extreme this tour has already crossed lives inside that thin sliver. The sun's furious surface, Triton's frozen nitrogen ground, the Boomerang Nebula colder than the cosmic background itself, all of it belongs to the small fraction of the universe actually built from something. Step into the space between the filaments, and none of that applies. There is no photosphere out there to burn, no nitrogen ice to crack underfoot, no dying star flinging its own outflow, cold enough to beat the background, the way the nebula managed. There is only the background itself, doing what it does everywhere, filling a room with almost nothing else in it. Inside that empty room, something still sets the temperature. It is not starlight. There is almost none of that out there. It is not drifting interstellar gas. There is almost none of that either. It is the same afterglow this story keeps returning to, the cosmic microwave background, 2.725 Kelvin, doing alone in the voids exactly what it does everywhere else, filling the emptiness and answering back into it. No star to compete with it. No cloud of warm gas to drown it out. It is the only thermostat this emptiness has, and it runs the whole room by itself. And even that thermostat keeps falling. Roughly every 100 million years, the background radiation cools by another sliver, stretched thinner as the universe keeps expanding around it. The same slow stretching that has been thinning it since the fireball first went clear. There is nothing in the void to slow that fall. No star to flare and warm a corner. No cloud of gas to hold heat a little longer before letting go. Only the patient arithmetic of expansion, cooling a room that was already nearly empty and already nearly cold, and will simply keep cooling, with nothing in it to object. This is the same one-way fall this story named at the very start. The CMB dropping degree by degree toward an ending too distant to picture. Only here, in the voids, there is nothing at all standing in its way. Galaxies, stars, planets, the whole glittering exception this tour has spent so long walking through, sit scattered across that larger room like the last few embers in a dark house at 4 a.m. The house is the rule. The embers are the exception. And embers, as anyone who has banked a fire overnight already knows, do not glow forever. What happens when they finally go out is a story that reaches further than any void, all the way down to the stars themselves, and even further to the black holes that outlive them. Black holes were supposed to be immune to it, immune to everything. For most of the history of physics, they were treated as the coldest objects that could exist, absorbing light, matter, and energy and returning nothing. Their boundaries, perfect one-way doors. Whatever fell in was gone. Whatever reached the edge stayed on the other side. An event horizon, physicists assumed, radiates nothing at all. It was the ultimate cold sink, a thermodynamic dead end where the story of every particle that fell in simply stopped. In 1974, everything changed. Stephen Hawking combined general relativity, the physics of gravity, with quantum mechanics, the physics of the very small, and found that the old assumption was wrong. Black holes are not perfectly cold. They glow, faintly, at the very edge of what is possible. Quantum effects near the event horizon, the point of no return, let a trickle of particles escape, a whisper of radiation now named for the man who predicted it. Not silent, not sealed, radiant, however faintly. The glow depends on mass. Smaller black holes run hotter, larger ones run colder, and a black hole carrying the mass of the sun, a sphere barely wider across than a small town, comes out at about 6 times 10 to the -8th power Kelvin, 60 billionths of 1 degree above the floor of everything, more than 40 million times colder than the 2.725 Kelvin background it sits inside. At that temperature, the black hole absorbs more of the cosmic microwave background than it gives off. Right now, it is still gaining, not losing. For that to reverse, the background itself has to cool below the black hole's own whisper of heat, and the background is only 2.725 Kelvin, falling by the barest fraction every 100 million years. It will take a very long time, but the universe has a very long time. Once the background finally drops low enough, the black hole starts losing more than it gains. It shrinks. As it shrinks, it heats. Smaller always means hotter, and the shrinking and the heating feed each other, faster and faster, until in its final instant, a black hole that spent unfathomable stretches of time as one of the coldest things in existence ends in a burst of radiation and violence, tiny in total energy but staggering in temperature, cold to hot in one last act. That glow opens a harder question underneath it. When something falls into a black hole, its information, the exact quantum details of every particle it was built from, appears to vanish behind the horizon. If the black hole eventually evaporates completely, where does that information go? Physics insists it cannot simply be destroyed. Hawking wrestled with the problem for decades and changed his position more than once. The current best guess is that the information survives, smuggled out inside the radiation itself, scrambled past any hope of reading it back, but not erased. The exact mathematics of how is still being worked out, decades after the question was first asked. Either way, something endures. We do not yet know exactly how. Black holes are not the only objects the universe eventually cools. When a star far more massive than the sun, something upward of 8 or 10 solar masses, burns through its last fuel, its outer layers detonate outward as a supernova, and its core collapses into a neutron star, a sphere no wider across than a mid-sized city. At the instant of collapse, its temperature exceeds 100 billion degrees Fahrenheit. This tour has already used the sun's blazing surface, nearly 10,000 degrees, as its hottest touchstone. A newborn neutron star runs past that mark by a factor of 10 million. Matter this compressed weighs on a scale that barely makes sense. A single teaspoon of it would weigh roughly 1 billion tons. And still, it cools. In its first seconds and minutes, a neutron star sheds energy through neutrinos, ghostly particles that barely interact with anything at all, at a staggering rate. Over thousands of years it settles to millions of degrees. Over billions of years it settles further. Given quadrillions of years, even a neutron star radiates away nearly everything it has. Its fierce magnetic field long decayed, any material it once pulled in long since stopped falling, until it settles quietly into the background it was born so far above. Everything cools. Everything eventually moves toward the cold. What ties all of it together is entropy. In practice, entropy is a measure of disorder, how many ways the pieces of a system could be rearranged and still look the same from the outside. In consequence, it is the reason time only runs one direction. The second law of thermodynamics says that in a closed system, entropy only ever grows. Heat flows from hot to cold, and never spontaneously the other way. Drop a piece of ice into a warm room and warmth flows into the ice until both settle at the same temperature. The room never spontaneously grows warmer while the ice grows colder. Not once, not ever. No matter how long you wait. Structure decays. Differences smooth out. It is not a tendency physics sometimes honors. Across everything ever measured, it has never once been broken. Every temperature difference in the universe is a reservoir of usable energy. A star is a gradient, a furnace of plasma pressed against the cold of space. A body is a gradient too, a warm engine running against a colder room. Life on this planet exists because of one gradient in particular, the sun's roughly 9,000 degree surface, pressed against the 2.725 Kelvin of deep space. And every heartbeat, every thought, every gust of wind draws on that difference. Not the heat itself, the difference. A world sitting at a single uniform temperature, however warm, could not power a single storm or grow a single leaf, because nothing would have anywhere left to flow. Spend the gradient, and the difference disappears. Spend enough of them, everywhere, forever, and nothing is left to spend. That is heat death. Not an explosion, not a collapse. The quiet, patient conclusion of a law that has never once failed to apply. Stars burn out. Neutron stars cool past detection. Even black holes, the last holdouts, finish evaporating. A solar mass, one needing something on the order of 10 to the 67th power years. A 1 followed by 67 zeros. A 68-digit number, set beside a universe that is 13.8 billion years old. A 10-digit number by comparison. And after that, after every gradient in existence has finally leveled out, the far larger heat death arrives. Somewhere around 10 to the 100th power years, a 1 followed by 100 zeros. What remains afterward sits close enough to absolute zero that the difference stops mattering. The direction has never once reversed. Every moment since the beginning has been a little colder than the one before it. What burns now, what beats now, what thinks now, is a brief, warm departure from a rule the universe has otherwise followed without exception. To understand how rare and how brief that departure really is, it helps to go back to where the warmth first came from at all, back past every star this tour has visited, to the very beginning, when the entire universe was hotter than any number can really mean. Start there, at a number too large to hold onto, and let it unfold in order instead. Not an explosion going off inside space. The beginning of space itself, and of time along with it, the first instant either one existed at all. In the smallest fraction of a second, the temperature climbed past 10 to the 32nd power Kelvin, a value physicists call the Planck temperature, the highest number that still means anything under the laws we currently understand. Above it, gravity itself is thought to behave like a quantum particle, flickering and uncertain the way light and electrons do, and no theory yet describes what that looks like. We do not know what happened at that temperature or before it. The trail simply ends there, exactly where the heat was at its worst. Every cold thing this tour has measured, the black holes, the neutron stars, the void itself, is downstream of that single unimaginable instant. A long exhale that has not finished yet. How does anything cool down from a start like that? It never really stops. Within the first second, the universe had already cooled to something like 10 billion degrees, hotter still than the collapsing heart of a newborn neutron star, but a small fraction of what came before it. A dense plasma of protons, neutrons, electrons, photons, and particles that do not survive anywhere in the universe today. Within the first 3 minutes, it had cooled further, to around 1 billion degrees, cool enough finally for protons and neutrons to stop bouncing apart and start sticking together. Hydrogen nuclei formed, helium nuclei formed, a trace of lithium formed. This is called Big Bang nucleosynthesis, and it produced nearly all the hydrogen and helium that exists anywhere. The hydrogen atom in your body, in the water you drink, in the fusion burning right now at the heart of the nearest star. All of it traces back to those first 3 minutes, forged while the universe was still cooling out of its own fire. No heavier elements existed yet. There was nothing to make a planet from, nothing to make a rock from, nothing to make a person from. Just hydrogen, helium, a trace of lithium, and a universe still glowing too fiercely to see through. For the next 380,000 years, the cooling continued, but the universe stayed sealed, a fog of charged particles too dense for light to travel far before scattering into it again. It glowed everywhere and revealed nothing. Then, at 380,000 years, the temperature had fallen to roughly 5,400 degrees Fahrenheit, about 3,000 Kelvin, cooler by then than Jupiter's crushed interior, but still hot enough to keep every atom stripped apart, until, at that exact threshold, electrons finally settled into orbit around protons. Physicists call the moment recombination. Neutral hydrogen formed for the first time, and the fog lifted. Photons that had been trapped since the beginning were suddenly free to travel in a straight line, and they have been traveling ever since. 13.8 billion years later, stretched by the universe's own expansion from visible light into microwaves. Cooled from 3000 Kelvin all the way down to 2.705 Kelvin. Those same photons are what a horn antenna in New Jersey once picked up as an unexplained hiss. The cold this tour keeps returning to is not only a temperature, it is a photograph, still developing, of the exact moment the universe first became see-through. What followed was transparent, but transparent is not the same as lit. For hundreds of millions of years, there was no star anywhere. No galaxy, nothing giving off light of its own, only vast drifting clouds of hydrogen and helium, cooling further in the dark, and the fading afterglow of the fog that had just lifted. Slowly, unevenly, gravity did what gravity always does. Denser patches pulled in more gas than their neighbors. Those patches pulled in more still, collapsing under their own weight, heating as they fell inward. This took tens of millions of years. Patient and unhurried, gravity working on clouds with nowhere else to be. Somewhere between 100 million and 200 million years after the beginning, in the densest of those collapsing clouds, the crushing and the heating finally reached the threshold for nuclear fusion to ignite. The first stars turned on. No telescope has ever seen one of those first stars directly. They are too far, too faint. Their light stretched too thin by billions of years of expansion to register on any instrument built so far. Though the James Webb Space Telescope, already the coldest instrument this tour has described, is searching for exactly that light now. What theory predicts about them is strange. Built from nothing but hydrogen and helium, with no heavier elements yet mixed in, some of them may have carried tens or even hundreds of times the mass of the sun. Stars that large burn recklessly fast. 1 million years, maybe less, and they were gone, tearing themselves apart as supernovae, scattering the first carbon, oxygen, silicon, and iron out into the surrounding gas. Every heavier atom in every planet, every rock, every living thing, waited for that first generation to live fast and die violently before it could exist at all. The universe had to lose its first stars before it could gain a single grain of dust. As those first stars burned, their light did something the cold dark had not seen since the fog first lifted. Ultraviolet radiation poured outward and stripped the electrons back off the neutral hydrogen surrounding each one, reionizing it, star by star, bubble by bubble, until the bubbles merged and the whole universe was ionized again, roughly 1 billion years after the beginning. Put that way, it sounds like the universe warming up. It was not. The deep background cold, the same 2.725 Kelvin this tour keeps returning to, never left and never even dipped. The stars did not warm the universe. They lit small, brief, brilliant exceptions inside it. Every star is an island. Every galaxy is an archipelago. And between them, filling everything, the cold holds. Exactly as old as the universe itself, and exactly as patient. That patience, it turns out, does not only destroy. Some of what the cold touches, it keeps. A freezer at home does the same small trick, slowing the chemistry that would otherwise break food down within days. A climate-controlled museum case does it for a fragile manuscript, holding the ink and the fibers steady for centuries longer than a shelf in an ordinary room ever could. A biological sample dropped into liquid nitrogen does it for tissue that would decay within hours at room temperature, freezing its chemistry in place rather than letting it run forward. In each case, cold is not stopping time exactly. It is only slowing the reactions that erase the past, giving them less energy to work with, fewer collisions to build on. So what happens when that same simple trick runs not for a few decades in a climate-controlled case, but for the entire age of the solar system, with no curator checking on it, and no freezer door ever opening? Out in space, the same simple trick operates on a scale that makes a museum case look almost trivial, and what it has kept, patiently, without anyone tending it at all, is extraordinary. Consider a comet. Underneath the ice and dust and loosely bound rock, a comet is ancient debris, an irregular body of ice, dust, and organic compounds that condensed out of the swirling cloud of gas and dust the solar system was still assembling from, roughly 4.5 billion years ago. Comets spend almost all of their long lives far from the sun, drifting through the Kuiper Belt or, farther still, the theoretical Oort cloud, held at temperatures where chemistry barely moves at all. Because of that, their interiors have scarcely changed since the solar system was young, cold holding their chemistry in place across the entire span of that history. When gravity nudges one into an orbit that finally brings it close to the sun, the surface ice warms and turns straight to gas without ever passing through a liquid stage, venting outward as the glowing coma and tail that make comets visible from Earth. But that surface loss is a thin skin, coming off an ancient body. The interior, still shielded from any real warmth, stays frozen and essentially untouched. Scientists have learned to read comets the way you might read a sealed letter. The molecules locked inside are the same molecules that existed, while Earth itself was still gathering out of smaller rocky fragments, called planetesimals. Here is where the story gets its sharpest proof. Between 2014 and 2016, the European Space Agency's Rosetta mission orbited comet 67P Churyumov-Gerasimenko and dropped a small lander onto its surface. Among the gases venting from that comet, Rosetta detected glycine. Glycine is an amino acid, the simplest one in the standard genetic code, a basic building block of every protein in every living cell on this planet. It almost certainly formed through the same slow tunneling chemistry, built one atom at a time on frozen dust grains inside a molecular cloud, that this tour has already traced elsewhere. And then it sat, locked in ice, for the entire history of the solar system, untouched by all 4.5 billion years that followed, while stars formed and planets cooled, and on at least one of those planets, the same molecule went on to become part of every strand of protein a living body would ever build. Cold only destroys, freezes, and shuts things down. Not quite, not always. Cold, done patiently enough, holds a molecule of life steady across a span of time that dwarfs the whole history of life on Earth, waiting in the dark for something, someday, to come along and notice it. If a comet is a sealed letter, The Oort cloud is the archive that holds millions of them, unopened. Picture a vast, roughly spherical shell of icy bodies believed to surround the solar system at distances ranging from several thousand times. The distance between Earth and the Sun out to perhaps 100,000 times that distance. Its outer edge roughly 1 to 2 light years out, nearly half the distance to the nearest star. Those objects likely formed much closer to the Sun, in the crowded region where the giant planets were taking shape, and were flung outward long ago by that same gravity, scattered to the far edge of the solar system's reach, farther than any spacecraft launched so far has managed to travel in a single human lifetime. Out there, at temperatures pressed close to this whole tour's returning number, 2.725 Kelvin, they have drifted for 4.5 billion years, preserved, lightly weathered on the surface by cosmic rays and starlight, but frozen solid at the core, holding chemistry from before the sun itself had finished forming, older than any rock a human hand has ever touched. We cannot reach them, not yet, and not with anything we currently know how to build. Voyager, still the fastest object humanity has ever sent outward, would need something like 300 years just to reach the inner edge of that shell, and tens of thousands of years more to cross all the way through it. Nobody alive today, and nobody's grandchildren, will ever hold that ice in their hands. But it is out there anyway, patient rather than empty, an archive rather than a wall, holding pristine early solar system material on a timescale that makes any human waiting look like nothing at all. The cold that ends so much, it turns out, spends just as much of its time quietly keeping watch. And there is more of that same cold still to map before this journey is finished. That map, it turns out, was never going to fit inside one number. Cold is not a single condition spread evenly across the universe. It has geography, the way a planet has geography, with regions that behave nothing like their neighbors, even when a thermometer would call them equally cold. Start at the sun. Its visible surface burns near 9,140 degrees Fahrenheit, and above that surface the corona somehow runs into the millions, hotter the farther out you look. A question this account has already admitted nobody has fully solved. Move inward toward Earth and matter settles into a temperature where molecules can bond and unbond freely, where chemistry and eventually life become possible. Move outward, toward the planets already toured, and cold enough to freeze carbon dioxide and nitrogen solid becomes the ordinary weather. Move further still into interstellar space, and the reading drops to 2.725 Kelvin, the same number this whole account keeps circling back to. Push into the shielded heart of a dense molecular cloud, and it falls again, to 1 Kelvin or below, the temperature already found waiting inside the Boomerang Nebula. And in a handful of physics laboratories on Earth, in chambers built for exactly this purpose, the reading has been pushed down to 100 picokelvin, a fraction of a billionth of a degree above the absolute floor, colder in that one tabletop container than any patch of the actual universe has ever naturally managed to become, including the frozen heart of that nebula. Each of those regimes runs on different rules, not just a different number on the same scale. In the corona, matter stops being solid, liquid, or gas at all, and becomes plasma. Electrons stripped loose from their atoms, everything charged, everything interacting through electric and magnetic fields instead of chemical bonds. In the sun's visible surface, temperature ionizes some atoms and leaves others untouched, carving the exact pattern of missing light that astronomers read as a chemical fingerprint. At room temperature, molecules hold together loosely enough to react but tightly enough to build something lasting. The narrow window this whole story keeps calling life's chemistry. Out past the planets, that same hydrocarbon chemistry runs slower and stranger, laying down lakes of liquid methane instead of water. At 1 Kelvin, ordinary collision stops driving reactions altogether, and quantum tunneling takes over instead, building molecules one impossible step at a time. At 100 picokelvin, quantum mechanics, normally invisible at any scale a hand could touch, starts operating on objects large enough to see. The universe does not have one cold. It has many colds, each with its own physics, and this account has now stood inside every one of them. The doorways between those regimes are not gradual. They are called phase transitions, sudden reorganizations of matter at a specific threshold, and the universe's whole history can be told through them. Roughly 380,000 years after the beginning, cooling let electrons finally settle into orbit around nuclei, and the universe flipped from an opaque plasma into a transparent gas within what amounted to a single cosmic afternoon. Liquid helium, cooled to 2.17 Kelvin, just half a degree colder than the interstellar background itself, stops behaving like an ordinary liquid and becomes a superfluid, flowing without friction, climbing the walls of its own container. Certain metals, cooled to within a few degrees of absolute zero, lose all electrical resistance and become superconductors. And earlier than any of that, in the first tiny fraction of a second, as the universe cooled below something on the order of 10 to the 15th power Kelvin, hotter than the collapsing heart of a dying star by a factor with 15 zeros trailing behind it, the electroweak force split into the separate forces of electromagnetism and the weak nuclear interaction. Before even that, at temperatures higher still, the strong nuclear force broke away on its own. 13.8 billion years of phase transitions, each one handing the universe a new set of rules to run on. We live inside one particular result of that long cooling, the phase where stars can burn and planets can form, and chemistry can fold itself into something that thinks. One particular phase. Not the only one. Not a permanent one. Here is the part worth sitting with. Cold has been treated across this whole account as the threat, the thing that kills an unprotected traveler, seizes metal, stores chemistry, waits at the edge of every warm system to take it back. And for a fragile body in an unheated vacuum, that is exactly true. But there is another way to see the same relationship, and it changes what cold means entirely. Life on Earth does not run on the sun's heat by itself. It runs on the difference between the sun's roughly 9,000 degrees and the cold of space pressing in at around 455 degrees below zero. That difference is the engine. Sunlight arrives, warms the ground and the ocean and the air, and radiates back out into a sky that sits almost at absolute zero, and it is the flow across that gap, not the heat sitting still on either end, that drives weather, ocean currents, and the chemistry inside every leaf turning light into sugar. Take away the cold and the gradient collapses. A universe with no cold anywhere would be a universe in equilibrium. The sun's warmth and the void's chill evened out into one flat, useless temperature, and a system in equilibrium does nothing. It does not build, react, circulate, or live. Cold is not the opposite of the engine that makes life possible. Cold is one half of it. There is a reason the universe leaned so heavily toward cold in the first place, and the physicist Ludwig Boltzmann, who died in 1906, worked out why. Temperature, in his account, is a matter of probability. A hot, ordered arrangement of matter, a star, a planet, a living cell, is one arrangement out of an almost uncountable number of possible arrangements, and nearly all of the others are cold, disordered, and spread thin. The universe drifts from hot to cold, and from order to disorder, not because cold is somehow more fundamental, but because there are staggeringly more ways to be cold and disordered than there are ways to be hot and organized. And given enough time, the more probable outcome simply happens more often, which means every hot, structured, complicated thing in this account, every star, every planet, every living cell, is a statistical anomaly, an improbable exception squeezed out of a universe old enough and large enough for even wild improbabilities to occur. A molecular cloud happened to be dense enough to collapse. A planet happened to sit at the right distance from its star, held steady by the pull of larger planets farther out, and a moon large enough to keep its axis from wandering. And on that planet, sustained entirely by the gradient between a hot star and cold space, life happened. Not the expected outcome of a universe built for it. An accident the universe was old enough and patient enough to eventually produce. None of that is a reason for despair, whatever it might sound like at first. It means this planet, this warmth, the chemistry able to look up and wonder about its own origins, was never guaranteed and was never the point of anything. It is a fluctuation, a brief, improbable structure inside a universe that runs overwhelmingly cold, empty, and quiet. And that fluctuation still found a way to produce art, music, curiosity, the very questions this account has spent so long trying to answer. Every experience anyone has ever had, in the end, traces back to a temperature gradient, a hot star and a cold sky, and a narrow zone of chemistry organizing itself in between, long enough to notice both. The honest picture of cold was never really about how it kills an unprepared traveler or slows a spacecraft's instruments, though it does both of those things. The honest picture is that cold is the universe's resting state, the baseline every scrap of warmth and structure only ever borrows time against. We are living inside the borrowed time. We are the exception, and someday, billions of years from now, the exception will end. The sun will exhaust itself and go dark. The earth will cool past any temperature that can support what stands on it now, and the cold will return to exactly where it has always been, 2.7 degrees above absolute zero, and still falling, patient the way it has been patient since before there was a sun to lose. The second law says disorder always wins in the end, and it will, but not yet. For a window, still billions of years wide, a star burns, a planet stays warm enough to hold water and weather and living things, and a fragile, astonishing arrangement of chemistry keeps looking up into that cold, still trying to understand it, still finding it beautiful rather than only bleak. The cold was here before the first star lit, and it will be here long after the last one goes dark. But right now, for this one brief and improbable stretch, something warm enough to notice is looking back,